Hi everyone, I am going to go through topic 4 and topic 9 in a way where I'm going to group all the topic 4 and 9s that are not related to interference first, and then I'm going to go through the portion on the topic 4 and 9 that are interference related. So this is how I'm going to go through topic 4 and topic 9 so that it's more relevant and more coherent as a whole. So I'm going to go through topic 4.1 first. And topic 4.1 is going to cover this, 4.1 and 9.1 is going to cover SHM. The central equation for SHM is this: A equals to minus omega square x. You need to know that all SHM motion all motion that satisfies SHM is this. It must follow this equation. Very important, you need to know that this is always measured from equilibrium position. Now, most of the questions that has tricks in it will be giving you x measured from some other places. So you must remember that x is always measured in all parts, all equations in SHM is always measured from the equilibrium position. Now, A over here is acceleration and omega over here is angular frequency. The other tricks that I can play with this equation is to give you force. A force against x graph or a net force against x graph. So the difference between this net force and A is that you've got to convert information over there to acceleration, so that before you can sub it into this equation. If you sub force straight into here, net force straight into here, you get it wrong. Now the difference for this one is that this is not net force, so you need to convert this. Usually they'll give you another force that acts on the system, so you need to convert this to net force minus away all the forces that are acting on the body, and then divide it by mass in kg, remember, and then before you substitute into this equation. So you need to know that how to manage this equation and to find the relevant, usually it's omega and then frequency or period. Next thing, you need to know from this equation that A and X are always in antiphase. So A and X, if A is a sine graph, then X is a negative sine graph. So it is an antiphase graph. So please remember this phase relationship, not just the numeric relationship, but the phase relationship between A and X. Now the next thing that you need to know is if you solve this equation, you're going to get X in terms of time. So X in terms of time will be X equals to X naught cos omega t equals to X naught sine omega t. You need to know when to use which. Please use this when you start the timing, when the object is at the extreme position. And you use this equation when you start the time when the object is at the equilibrium position. So the starting condition determines which one you use. And the thing is that if you differentiate this with respect to time, you will get V, which is omega x naught sine omega t, minus, if you differentiate the second one, it will be, without the minus, it will be cos omega t. Let's use the one which is sine, so it corresponds to this one. So if you were to take a look at this, xt graph will be sine and vt graph will be cosine. Now, two things you need to know. First, the amplitude over here is x naught, whereas the amplitude over here. So this is the Vmax. That's the maximum speed of anything going through SHM, and it always occurs at the equilibrium position, which I'll show you how to derive it later. And the other thing is that you need to know that between this and this there is a 90 degrees phase difference. This is probably quite easy for some of you who are strong in mathematics, because this and this, sine and cosine, they are 90 degrees apart from each other. How do you know? You shift this towards the left by 90 degrees, you get this. And this also leads to the next point. Which of them leads which of them? Very simple. This is always the way that you go about looking at things. The one that reaches the maximum position first, earlier in time, will be the one that's leading. So since V reaches the amplitude first as compared to this by 90 degrees, we say that V leads X by 90 degrees. Alright? And if you were to differentiate this, A equals to, say for example, this to this, you'll be minus omega x naught, or minus omega square x naught sine omega t. So therefore, what you have over here is that if you got an A, it will be like this, T, A. So which one leads which one? It is still A leading V, because if you extend the graph over here, you'll see that A reaches the equilibrium, the maximum earlier than V. So this leads this by 90 degrees, A leads V by 90 degrees. Okay, so this is what you need to know for the X, the defining equation for SHM, the X T graph, V T graph. The next thing you need to know is this relationship between V and X. You need to know that V and X, they are related by this equation. It is in the data booklet. So this equation shows you two things. First, that when X equals to 0, V equals to a maximum value. Why? Because this is always positive with square. Positive or negative is always a positive number. So you minus a positive number, it will always be smaller. The next thing, V max is equals to omega X naught, as we would have predicted over here. So this equation also takes the same thing. You need to remember that X is always measured from the equilibrium position. Okay. Next thing, we talk about energy. There are two things that can come out for energy. First thing is you need to know this equation, that K max is equals to half m V max square, which is half m omega square x naught square, which is also equals to the total energy, because the K in an oscillating system, the total energy always oscillates between the K and P. So the K max is also the T, which is also the P max. So you need to know that the P total energy is proportional to x naught square and also omega square, and also of course m. But usually the thing that changes is this. Say for example, a typical IB question would be, if the x amplitude were to be doubled, what would change? What would be the effect on the omega and the total energy? So you need to know that it is part of the syllabus to know that for spring mass system it is this. It is in the data booklet. For a pendulum, it is this. So nothing to do with amplitude for period, so it doesn't affect. But the total energy, if you double the amplitude, it will be 4 times the energy. So you need to know this relationship between total energy and the amplitude or the frequency. All right. The next thing, graphical. You need to know how to sketch the energy against X graph. It looks like this, and like this. This is total energy. Maximum energy at the equilibrium for kinetic energy, maximum at the ends for potential energy. Second thing, for about energy time graph, we shouldn't go negative. One very important thing is that you need to know that if this is 1, 2, 3, 4, the period is 4 seconds for this motion. Why? Because 2 cycles of energy graph is 1 period. Now one thing that you can understand, the way that you can understand this is quite simple. Say for example, if you've got a V graph that looks like this, this way. So if this is V against time, if I were to do KE, what I do is that I square this. So it will look like this. So as you can see, a V squared graph, which is proportional to the related to the two kinetic energy, it will be 2 periods, 2 cycles in 1 period. Okay, so please remember this, really important. So with this, we have gone through 4.1 and 9.1. Next thing I'd like to go through is 4.2 and 4.3. It is the easier part of waves. In fact, 4.2, I'm not going to spend too much time because 4.2 is really secondary school stuff. Let me show you. 4.2, all you need to know is the definition of amplitude, period, frequency, speed, and wavelength. And also these few very familiar equations that you must have seen before. So please refer to your notes. I'm not going to elaborate too much on this. But something more tricky is this. Say for example, if I got a xt graph, is this particle moving up or down? Say it is a transverse wave. So as the wave moves past, it goes up or down. Now, the way to go about finding out whether this particle moves up or down is to find if this is a time axis. Be very careful, look at the axis over here. If this is time axis, always follow to the next point of time, because there's only one way the particle can move in time. So it goes in this direction in time, in fact this direction, so it is moving down. So it is moving down. Is it accelerating up or down? Very simple. Every particle on the on a wave moves with SHM. SHM, remember, the acceleration always points towards the equilibrium. So this is how you find the direction of velocity and acceleration for a xt graph. Now, the more difficult part of this is if this is a xd graph. there is no way you can tell where the particle here is moving. I need to tell you something, which is if the wave is moving this way, then you shift the whole wave towards the left and the particle goes down. Likewise, if I shift the wave towards the right, if the wave is moving towards the right, then it will go up. So it depends on this, if this axis is given. So you must be very clear before you do anything, look at the axis. Alright, the next thing about this wave, this topic that you need to know, which is a little bit trickier than O-level stuff, is this. For longitudinal wave. So if I got a displacement distance graph, I got a wave that looks like this. So longitudinal wave is a little bit naughty because it oscillates this way as the wave moves this way or this way. So say if we define rightwards motion as positive, what does it mean? It means that this particle is displaced positively, this particle displays a lot, positive, this particle over here is displaced negatively, a lot of negative displacement, a little bit, positive displacement, loads of positive displacement. So you need to map out the motion of the particle. Is it displaced towards the right or left? Second, you need to identify the compression and rarefaction. Compression is always the point, or rarefaction are always the y-intercept. And how do you determine it? When the particles come together, it is a compression. When the particles go away, it is a rarefaction. So very easy for you to identify the compression and rarefaction. So as the wave moves towards here or here, the compression and rarefaction actually moves along, which is what we expect. So this is 4.2, very simple. 4.3, a little bit trickier. 4.3, the more difficult part of 4.3 is the polarization. You need to define this. You can check on your notes. Define what is meant by polarized wave. Define what is meant by polarization. You need to know Malus law. Now, Malus law, I equals to I naught cosine squared theta. Mathematical question, so quite simple. You also need to know that intensity equals to half of intensity if unpolarized wave passes through polarizer. So you need to know this relationship here. Half the intensity if unpolarized wave passes through polarizer. And if it is polarized to polarized, use Malus law. Theta is the angle between the plane of polarization of the light or the wave to the axis of polarization of the polarizer. Alright, now this is the polarization aspect. And you also need to know that reflection polarizes the wave. The wave that is reflected will be the one that is polarized, mainly parallel to the plane. So if this is unpolarized, wave oscillating, electric field oscillating in all directions, the wave that bounces off, it is predominantly polarized in the plane that is parallel to the plane of the object that you're reflecting it off. So this is polarization by reflection. Of course, the other one that we talk about is polarization by polarizer. Now the other thing about 4.3 that you need to know is if wave were to reflect off a open end. So say for example, if a wave, okay, probably I give a more defining wave, say like this. Weird wave, but let's say it goes to an open end over here. So when the wave reflects backwards, how does it go back? Now if it is an open end, it doesn't exert any resistive force. So if it reflects, this is going to be the first one to reflect, so it just reflects this way. Very easy. So for open end, just reflect it this way and goes this way. So, but for a closed end, the tight end, if a wave were to move this way, now not only does it get reflected, because this is going to be the one that's reflected, because it's tight end, it exerts a force in the opposite direction on the string as this hits the wall. So it is going to be like this. So just remember that if it is a tight end, reflect it this way and reflect it this way again. Alright, so this is reflection of an open end and a tight end. So that's it for 4.1, 9.1, 4.2 and 4.3. I'm going to go through 9.5 first, then I'm going to come back to 4. Or why not I just go through 4.4 now. 4.4, there are two parts. One part is the Snell's law part, that's the easier one. And the other part is the more difficult one, is the interference. That one I'll leave it together with 9.2, 3 and 4. Alright, that will come together so that it's a whole package. At 4.5 as well, standing wave. So I'm going to go through 4.4, the easier part of things. Now the 4.4, the easier part will be the part on the Snell's law, as I mentioned. So n1 sine theta 1 equals to n2 sine theta 2. How do you use this? Very easy. In fact, this is more complete than the one that you learned in O levels. So if you've got region 1, region 2, and n1, n2, theta 1, theta 2, it is related by this equation. This is the complete form. It works even when you want to derive it for the critical angle. So it works for all situations. You don't have to remember which one is denser, which one is less dense. You just need to be consistent with your n1 theta 1, n2 theta 2. Second thing, you need to know n is defined by the speed of light in vacuum divided by the speed of wave in the medium. So you need to know the definition of refractive index, and also if total internal reflection happen, you need to know how to find the critical angle. Either way it works. So sine theta c equals to 1 upon n, or n equals to 1 upon sine theta c. Right, this is the easy part. Like what I said, the more difficult part will be covered in the next video on interference altogether. 9.5, which is on Doppler effect, very simple. You need to know how to define Doppler effect. It is in your notes. Please take a look at that. More importantly, you need to know that there are two cases: moving source and moving observer. This changes the wavelength. This changes the speed of sound. Whereas the speed of sound is constant, whereas wavelength is constant if the observer is moving. So you need to be very careful what is changed, resulting in the change in frequency. The other thing that you need to be careful is, of course, the sign that you use. So this is V of sound plus minus V of observer, V of sound minus plus V of source. Just remember, whenever you have the observer and the source moving together, say for example this one, and the source is producing the sound this way. So the way that you write or choose the equation, the sign, is to choose the sign by looking at the relative motion of the object and the observer and the source. Say for example, if you got the observer moving towards the source, regardless of how the source moves, you always increase the frequency. So you choose plus. Whenever the source moves towards the observer, regardless of what direction it moves, it always increases the frequency. So you choose this one. So you choose the frequency, you choose the sign depending on the relative motion. So long as they move towards each other, you always choose the sign that increases. If they move away from each other, you choose the sign that decreases. Alright? That's it. Actually, then one more thing, for wind that blows across between the observer and the source, you need to know that wind doesn't change the frequency, but it does change the wavelength and the speed of sound such that the frequency doesn't change. The collective effect due to the change in speed of sound and the speed of the wavelength, collectively it results in no change in the frequency. Alright, so with this we're only left with part of 4.4, 4.5, 9.2, 9.3 and 9.4, so which is the next video that I'm going to cover. I hope this will help you in your exams, a quick revision. So after this I'm going to go through the other parts of 9.4 and 9, and then I'm going to go through the ASP part of the what you need to know. Alright.